And also thanks to the organizers for giving me the opportunity to talk to you today. And welcome everybody to my presentation about solution state NMR spectroscopy of crystalline cellulosic materials. Short overview, I want to talk to you today about solution state NMR of cellulose. And more specifically, I wanted to talk to you about an NMR method that got developed here in Helsinki over the last years, which is using tetra-N-butyl phosphonium acetate DMSO-D6 mixtures to dissolve cellulosic materials and then measure solution state NMR of it. And some of you might have heard about it already. Also, Lars mentioned it in the lecture before. This method is not really new. It got developed in Helsinki University over a course of, I would say, almost 10 years. So the first reports date back 10 years or so. After they discovered that this solvent system has very nice properties for NMR applications, a team around Alistair King put a lot of effort in optimizing like the electrolyte system, optimizing the NMR part, and they came up with a very nice NMR method that got published already in 2018 in Biomacromolecules. You can find the reference on the bottom. And yeah, since 2018, Alistair presented it a lot in different scientific conferences. Also, the method got used in quite a lot of research papers already. I know at least 20, probably there's more. And yeah, so you could say this method is already quite established, at least here in Helsinki. But today I don't want to talk too much about the history or the development or the optimization of this NMR method, and also not in particular why this particular solution is so good for NMR spectroscopy, because I was not involved in all this research, and I'm also not a real expert on it. But if you're interested in that aspect of this NMR method, I can only recommend you to listen to Alistair's presentations. And there's a very easy way to do this nowadays, because he just gave a lecture for the Tree Search seminar series, and I can just recommend to you to look it up on YouTube. But then why am I presenting this NMR method then today? So basically I have a more practical approach to this topic, because I'm, as Julia mentioned, I'm a PhD student here in Aalto University, and I'm working on cellulose chemistry. And I also have a background in small molecular organic chemistry from my studies back in Innsbruck. And there in the lab, in my everyday work, I was used to just use solution state NMR a lot for like analyzing basically all my samples. And I liked it a lot. It is a very reliable technique, very powerful, very quick as well. And of course, I also wanted to have this analytical tool for my PhD studies. However, you cannot measure solution state NMR of cellulosic materials that easily, for the simple reason that cellulose is insoluble in most solvents, and especially in the deuterated solvents that you need for NMR applications. And as I moved to Helsinki, I contacted Alistair, and around 2 years ago or 2.5 years ago, together with Katja Heise, we asked if we cannot transfer the protocol from the developing experts in Helsinki University to a more cellulose technology and cellulose material focused research environment here in Aalto University. And when we did this based on the manuscript that got published in 2018, we saw that there are still quite many issues that do not allow an implementation in a less specialized research environment. And so we put a lot of effort in simplifying the workflows, addressing these issues. And now I can say it successfully works at Aalto University as well, this NMR method. And because we thought maybe other researchers are also interested in implementing this method, we summarized the journey of this process to an extensive protocol. And I may proudly present it got finally published last week in Nature Protocols, our solution state NMR cellulose protocol. And yeah, this is a very extensive article. It has 45 pages, and it has read a long introduction about the history and of this method and how it compares to other analytical techniques. And it has also like a protocol section where like the synthesis of the ionic liquid is discussed in detail, where the dissolution of the cellulose is discussed in detail, how to set up the NMR experiments, what you can see in the NMR spectra, and some like examples how you can use it in your research. So this protocol is really aimed for non-NMR experts, for every like cellulose researchers, cellulose chemists who want to use it on a day-to-day basis, so that they also can profit from the like significant or from all the possibilities that solution state NMR spectroscopy offers. And yeah, and I can just recommend to read through it, and like if you want to implement it, it's like 45 pages. I have 20 minutes, so I cannot get into every detail, but I just want to highlight some aspects why I think solution state NMR is really a great thing to have in the lab. Good. And I want to start like just by showing the high resolution that solution state NMR offers. We heard about this already in the last talk. And you can see on the bottom a solid state 13C NMR spectrum of an MCC sample, and on the top you can see a solution state NMR spectrum of the same microcrystalline cellulose sample. And as you can see, the peaks are much better resolved in the solution state, and that is not because we have like this super great electrolyte. No, it's like some intrinsic benefit of solution state NMR, which comes with the solvation of the moieties, and then the shifts go to the same ppm values. And in comparison, in the solid state, as we heard before, we have different moieties that all contribute to the peaks, and then you get like these broader peaks, which are very interesting, as we heard as well before. For example, if you're interested in supramolecular features of your samples. However, if you're only interested in the chemical composition of your samples, solution state is just intrinsically better. And also what I want to highlight, like this combination, or another benefit of solution state NMR is that the sample or the spectral acquisition is much faster in the solution state than in the solid state. And that means that also 2D NMR spectra are accessible, like high quality 2D NMR spectra you can get in a reasonable acquisition time and with great signal to noise and a great resolution as well. As we heard before, like it is rather complicated to get like 2D NMR in solid state, and in solution state that is quite easy, and it's quite easy, and you get very well resolved spectra. So for example, we have here HSQC spectrum, 1H13C HSQC spectrum of some low molecular weight cellulose model substance. And besides the unreduced or glucose units, you can also see the reducing ends and the non-reducing ends. And you can even see the different alpha and beta anomers of the reducing ends. And it also doesn't take very long to get such a high quality HSQC spectrum. You can normally get something like this in 2 to 3 hours. So that really allows now, like with this increased resolution, it really allows to investigate, for example, reactions of reducing ends as well. Alistair worked quite a lot on it. Heise did some experiments or published nice articles about this. And I also, in my experiments now, I found out that the chemistry of the reducing ends is rather interesting. And also with the solution state NMR method, it's actually not that difficult to investigate the chemistry of the reducing ends. And another point I want to highlight of this NMR method is like or from solution state NMR in general, is the accessibility of solution state NMR. So I'm not pushing NMR or a method that needs some synchrotron or some super specialized equipment. No, like this is NMR spectrometers normally can be found in almost all research institutes as long as you have somebody working on organic chemistry. And I also want to highlight that this protocol doesn't need any specialized equipment. It is usually good to go on a non-specialized standard spectrometer. Most universities have in their institutes. For example, I'm measuring on a normal 400 megahertz NMR spectrometer that did not get any like upgrades or any special treatment before we implemented the protocol. And also that means, like, because there's an MR spectrometers everywhere, there are also some experts who who use it on a daily basis, and that can help you with with following your MR experiments and also with the spectral interpretation if you need help with that. Good. Then I want to talk more specifically about this tetrabutylphosphonium acetate ionically NMR electrolyte. What makes this a good choice in general for solution state NMR applications for cellulosic materials? So it should be mentioned that there are other solution state NMR protocols available. Like most prominent, I would say, is like the indirect approach of a pair acetylation of the cellulosic materials and then dissolve it in standard deuterated solvents. There are also some reports on protocols using imidazolium ionic liquids. However, they are not that suitable for NMR applications. They are also did not get really developed further or did not develop a standard to follow, although the first reports date back already to 2004, 2005, I think. And what makes our NMR electrolyte a good choice is that the synthesis of the ionic liquid following the metatitis or synthesis schemes that are presented in the protocol are relatively easy and can be performed from cheap compounds you can only get from Sigma Aldrich. Also, we can use 80% of a deuterated co-solvent, which minimizes the peaks of the non-deuterated ionic liquid peaks. And also, we don't have any signal overlap between the cellulose and the ionic liquid peaks. So we have a free measuring range or free measurement area for our cellulose. And also, what is quite nice is that this electrolyte gives low viscosity solutions already at a temperature of 65 degrees. So other solution state NMR protocols usually take higher temperatures, and that means higher temperatures means that degradation reactions become more likely. And also, you need, if you want to measure at higher temperatures, you need more specialized NMR spectrometers, which is also like a downgrade if you want to push it as a standardized protocol. Good. And also another benefit is that the experiments is this building up know-how in this solution state NMR method. So some experiments got especially like fine-tuned to be that they are used for cellulose. For example, Alistair reported on this nice diffusion edited 1H experiment. And so basically what is the problem? If you look at the standard 1H experiment, you can still see the ionic liquid peaks and the DMSO and the water peaks that are, although they are not overlapping with the cellulose signals, they're still very prominent, and they reduce like the accessible spectral area. And by just performing a simple diffusion editing experiment, you can cancel out all the low molecular weight peaks in the spectrum. So you can remove all the ionic liquid peaks, all the DMSO peak, the water peak, and what you leave behind are only like the polymeric peaks in solution. And in the case of if you measure cellulose, it's mostly cellulose that remains in solution. And why this is very nice, or why I like this experiment a lot, it looks like a standard 1H experiment, like the experiment I used the most in my former university, like in my former studies on small molecules. And what is very nice, if you're like interested in chemical modifications of cellulose, then if you have a covalent modification of the cellulose backbone, you can easily see it on the diffusion edited experiment and distinguish it between like only impurities that might remain from insufficient washing, insufficient purification of your material. And you can see it because the modification on the polymer also is then a high molecular weight peak, and then you can see it. And also what what is nice if a protocol gets standardized is that I want to present or want to show again the HSQC spectrum you see before. And if like a standardized protocol is used, then you can build up on former reports that have been like former reports, especially peak assignments that have been done in previous studies. So for example, if this spectrum would have been measured in a different ionic liquid at a different temperature, the peak shifts would be similar, but not completely in the same area. If you always use the same protocol, the same measuring conditions, then you can only easily build up on former reports. Like for example, if you have like all these small peaks from the reducing ends and from the non-reducing ends, and you have another modification where possibly another small spin system comes in, it becomes visible in the spectrum, becomes difficult to distinguish like what peak belongs to which modification. And if you can build up on previous reports, it becomes quite easy, because then you know, yeah, I saw this peak before, and it saves a lot of time in like the peak assignments for new materials as well. And then I want to highlight the broad applicability of this NMR protocol, or of this NMR electrolyte. So here you can see like different cellulosic materials where this electrolyte was successfully used to investigate it. Like on the top, you can see low molecular weight celluloses, like the low TP model substance. We saw the HSQC spectra from the HSQC spectra, or like microcrystalline cellulose or sulfated CNCs. But although this method was initially developed for nanocelluloses and for low TP molecules, and it's also optimized for these cellulosic materials, the NMR or the electrolyte can also dissolve other celluloses, also high molecular weight celluloses. It can also dissolve other polysaccharides like xylans or mannoses, anhydrous units you can see here. Yeah, and that's so the electrolyte has a broad applicability and is not only restricted to the nanocellulose investigations that are often highlighted. Then also in cellulose chemistry, where I use this method a lot, I want to show you a study I did together with Jonas Simon from Boca University on the reductive amination of dialdate celluloses. And just quickly, there we screened different different congeners from dialdate cellulose, like reacted with different amines. And it is very difficult normally to distinguish like between these different materials. However, with solution state NMR, it became quite obvious only in the diffusion edited experiment which material belongs to which spectrum. And yeah, good. And also another application I want to highlight is like, or to show that it dissolves a lot, is like this mild repeated wood sample. So this NMR electrolyte can not only dissolve cellulose, but also different other constituents of wood that is also not optimized for these purposes yet. Will need some optimization, but it means in general you can also investigate other wood materials and also composite materials, and not only like polysaccharides or wood constituents are like soluble in the electrolyte. Also other materials I want to show, for example, proteins that you can find in foods, or like possible food from the future. And yeah, it's also not optimized for this. However, it just should show like the broad applicability, and it will also not reach like the same level as protein NMR we know from biochemistry applications. But for example, in composite materials, that could be interesting, or also in fingerprinting applications. Good. Some concluding remarks. Yeah. what I wanted to push today, I wanted to advertise our protocol, because I think solution state NMR is a very nice analytical method, very significant, and it had like a very big impact in different areas of research. And with this protocol, solution state NMR also becomes accessible now for cellulose research, and we think that is, yeah, might have a big impact as well. And one thing I want to highlight as well, like whenever I presented it or like talked about solution state NMR with like fellow PhD students who also work on cellulose and are not NMR experts, the first reaction I always get is always, yeah, that sounds so complicated and difficult. However, I want to really tell everybody who is interested in using it that this protocol in practice is really not that complicated. And you also don't need to know or that much about NMR or ionic liquid to successfully use this protocol. And I really want just to, like, if you're interested in it, I really just want to say, try it out, and you will be surprised how easy it is in practice. And also I want to mention for everybody who doesn't want to synthesize the ionic liquid themselves, recently we also found some company that can prepare the ionic liquid or the electrolyte in analytical quality. And if you want, if you don't want to synthesize it by yourself, then you can buy it and at Inotope under the name Cellulite. Yeah, and that was all from my side. I want to thank you for your attention, and I want to give special thanks to Alistair, who developed this method, to my boss, Michael Hummel, and to Katja and Tatjana, who were also involved a lot in writing this protocol and elaborating the workflows. And I also want to thank Jonas Simon, who collaborated in this project with the dialed celluloses. And if you have any further questions, please don't hesitate to write me an email or Alistair. And yeah, open for questions.